We are ready to talk about the fundamental theorem of calculus. We're first going to talk about part 1. The fundamental theorem of calculus is something that bridges the two main branches of calculus. We have differential calculus and we have integral calculus. Differential calculus is solving the tangent problem, finding the tangent to the curve at any given point, and we have finding derivatives. Integral calculus is finding the area under the curve, and we saw that led us to a definite integral. Isaac Barrow came up with this idea and found the connection between differential and integral calculus, and then he was the mentor of Isaac Newton, and Newton and Leibniz kind of grabbed onto that idea and used it as they further developed calculus. So let's see the idea behind this. First of all, we're going to look at g of x equaling the integral from a to x of f of t dt. And if we look at this and we have f of t being a positive function, then we can look at this as g of x equaling the area from a to x. So normally we're looking at the area from a to b, and we know that the integral, the definite integral from a to b, is the area under the curve when this function is positive. So we want to think of that as looking at some value x. So we're sort of part way to b, and we determine that x may change as we move along here. We are looking at the area from a to x. Let's go ahead and do this with an example first, and then we'll kind of see a connection here. So here we have a function whose graph is shown, and g of x equals the integral from 0 to x of f of t dt. Now our f of t this time is not always positive. We can see that by the graph. So we're going to find the values, the following. So we first have g of 0, and so that would essentially be from 0 to 0, the integral from 0 to 0, and so that's going to be 0. Then if we look at g of 1, we are looking at the integral from 0 to 1. So we are looking at this area right here, and we can see we have a triangle whose base is 1/2, whose height is 2. So 1/2 the base times the height, so that's going to be 1. So if we look at g of 2, so that would be our integral from 0 to 2. So we would have the area we had from 0 to 1, and then we would have this additional area, which is 2 more units. So that would just be 1 plus the 2 more, so that would be 3. Now let's look at g of 3. So that would be from 0 to 3. So as we go over here to 3, we would put on some additional area here. And this one doesn't work completely evenly, so we're just going to go ahead and do an estimate here. So I can see if I took a piece of this, I could fill in right here, and then there would still be a portion of this left. So adding on 1 more unit plus, about another third. So we're going to estimate that to be about 4.3. Now, as we figure g of 4, now we're over here, we have actually gone below, and so when we find the area here, this is going to end up subtracting from this 4.3, because as we compute the integral here, we would get negative values for things from 3 to 4. So kind of estimating this, we can see if we filled in this other piece with some of this and then determine what's left, it looks like that we would probably be taking off about the size we'd added on over there. So we'll probably be left with about 3. And let's go ahead and compute the last one here, g of 5. So we'd be integrating from 0 to 5 here, and this is also below the x-axis, and so the negative value. So I can see that this is going to subtract off about another 1.3 because it's symmetric and it's the same size as this one that I took off 1.3. So if I take off another 1.3 there, I would have 1.7. Now the other part of this is we want to sketch a rough graph of g of x, and we're going to do that looking at the values. We put in 0 through 5, so let's go ahead and get our rough graph. As we're looking at this, we can see at 0 we're going to be 0, and at 1 we're going to be 1. At 2 we're going to go up 1, 2, 3, and at 3 we're going to be at 4.3. Then at 4 we're going to be back down to 3, and then at 5 we're going to be at 1.7. So we can do something kind of roughly like this. Now let's see how these points correspond. So here is sort of what our rough sketch for what g of x would look like, and looking at f of t and seeing our corresponding points there. At 1 it was 1, but let's look at what is going on the curve between 0 and 1, and we can see that the slope starts out 0 and then positive, and it's getting steeper and steeper and steeper here. Well, look at this graph f of t, and we see that this value is climbing till we get here to 1. So what we're looking at is the slope of g, and we're seeing that that is what f is. Let's confirm that as we continue on and we look from 1 to 2. We can see that from 1 to 2 this curve actually has a constant slope of up 1, 2 over 1. So it has a slope of 2, and you can see that this graph stays on 2 between 1 and 2. So f of t is actually plotting the value of the slope of this curve. Let's look from 2 to 3. And we can see from 2 to 3 that we have a positive slope, but it's getting smaller and smaller until it gets to 0 when we get to 3. So here is this curve, the value of which is positive, but it is getting smaller until it gets to 0. Now, as we look at what's going on between 3 and 4, we see that we have a negative slope, and this negative slope is getting more and more negative as we get here to 4. So here is our negative value as we get here to 4. Now after 4, looking from 4 to 5, it's still a negative value, but it's not as steep as it was before, and it's heading towards 0. And so here we go. So what we've observed here is that if we have g of x equaling the integral from a to x of f of t dt, it appears that the derivative of g is f of t. So it looks like if we took this function and we took the derivative, it would basically undo this integral essentially and leave us this function f. Let's go ahead and look at a couple more things to kind of confirm this idea. Let's look at g of x equaling the integral from a to x of f of t dt then, where f of t is just some positive function. And so the integral from a to x would represent the area under the curve. Now let's look at another piece. If we add h to x, so we have x plus h, and we can look at this little area here, and we're going to look at that piece added on as a rectangle, and that rectangle would be h wide and f of x high, and so that area of that rectangle is going to be h f of x. So what we're going to do is say if we took the difference between g at x plus h, which would be the area under the curve to this point, and subtract off the integral from a to x, that's g of x, that would leave us approximately this rectangle. And the reason we put approximately is because of course this rectangle doesn't quite follow the curve, but it would essentially leave us this little piece. Now we could divide both sides by h, and we have g of x plus h minus g of x over h is approximately the function. But this is looking a little bit familiar. What if we took the limit as h approaches 0 of this? So here we have that, and we see that that is nothing more than the limit definition of the derivative. So what we've kind of seen intuitively here is part 1 of the fundamental theorem of calculus, which says if f is continuous on the closed interval from a to b, then the function g defined by g of x equaling the integral from a to x of f of t dt is continuous on a to b and differentiable on the open interval from a to b, and the derivative of g of x equals f of x. Now we are going to see a proof of this theorem. What we saw before was sort of an intuitive idea of what this theorem was going to say, but we will have an official proof of this following this video. But let's see essentially what this leads us to as far as what we can do with this knowledge. Basically what it's telling us is when we meet the conditions of f being continuous on this closed interval, and we have this function defined by the integral from a to x of f of t dt, then if we take the derivative of this integral, they essentially undo each other, and we are left with f of x. Use the fundamental theorem to find the derivative from a to x of cosine t dt, and that is just going to leave us the function then cosine x. So our idea is differentiation undoes integration when we've met this continuous function and when we are integrating from a to x. Looking at the second one then, as we integrate from 0 to x, so it could be any constant a to x, this would equal the function 1 over 1 plus x squared by the fundamental theorem, part 1. We will find the derivative if y equals the integral from x to 5 of 3t sine t dt. Well, the limits of integration are actually in the wrong order to apply the fundamental theorem. So we're going to turn that around, and we know by properties of definite integrals that we'd need to put a negative sign here and we would have the equivalent. So here we have the negative of the integral from 5 to x of 3t sine t dt, and now we can take a derivative of that, and if we take a derivative of that, we will get negative 3x sine x as the differentiation undoes the integration. Looking at another example, we want to find the derivative if y equals the integral from 1 to x squared of cosine t dt. Now here we have to be careful because on our limits of integration, instead of a constant for the lower limit, we do have that, but instead of the upper limit being x, we have a function of x. So when we take the derivative, the chain rule will apply. So we have the derivative of this is going to be cosine x squared multiplied by the derivative of the inside function, so multiplied by 2x. And let's look at one more example that kind of combines a couple of these ideas then. We want the derivative dy dx if y equals the integral from 1 plus 3x squared to 4 of this function. So we're going to need to first of all make this negative and reverse our limits of integration. And we still have 1 over 2 plus e to the t dt. Now we can go ahead and take the derivative, and the derivative essentially will undo the integral, except for the fact that we will need to apply the chain rule because we've got a function within a function here, and so we have negative 1 over 2 plus e to the 1 plus 3x squared, and we need to multiply that then by the derivative of this 1 plus 3x squared, which is going to be 6x.